Hello everyone, and thank you for attending today's webinar, Advances in EDS Throughput from X-ray Counts to Solutions. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all the questions. A copy of today's slide deck and some links to additional materials are available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the Maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the Help widget. It has a question mark icon and covers common technical problems. Finally, an on-demand version of the webcast will be available shortly after the live webinar, and it can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce our two presenters for today. Tara Nilis is the Global Applications Manager for EDAX. Tara works with EDS, EBSD, and WDS technologies. She started her career in microanalysis primarily with SEM-EDS-based techniques, and over the course of her 20 years with EDAX, she has incorporated the additional capabilities into her analytical approach. Tara holds a master's degree in chemistry with a professional science master's, which gives her an understanding of the commercial end of applied science and technology for the benefit of real-world industry and business solutions. Jens Raffelsson joined EDAX in 2014 as an applications engineer specializing in EDS. He has a strong background in electron microscopy and has trained numerous students and clients in SEM and EDS theory and practice. His experience includes several years as the technical supervisor of the cleanroom facilities at Aalborg University in Denmark. Jens earned his PhD in physics from Aalborg University. His research focused on germanium surfaces and nanostructures probed by nonlinear optical measurement techniques, photoemission spectroscopy, and electron microscopy. And now I'll hand over to Jens to introduce the webinar.
Thank you, Sue, and welcome to today's webinar. We will be talking about advances in EDS throughput, and we will start with some of the basics of the device structure itself. What do we actually measure, and what are the inherent limits to the throughput, and what we can actually do with the device? That's what we detect. The next step will be what we do with what we detect. We have a pulse processor in the signal chain as well, which also imposes some limitations in what can be done. So we'll talk a little bit about the pulse processor and what we're actually changing when we're changing the speed or throughput of our acquisition. After that, Tara will go through a few examples of what we gain when we change the processing speed, the step time changes, and how that relates to efficiency with a few different examples. One of them being a nickel titanium sample and a titanium aluminum vanadium sample, where we'll be looking at the quant numbers for the minor constituents, the aluminum and vanadium. Then I will go through a little bit of low energy and high speed at the same time, which also has a few practical limitations. And then we have a quick summary at the end of everything. But to get started, the silicon drift detector is basically a piece of silicon, about 500 microns thick, and we cool it down to somewhere between -10 and -50 degrees Celsius, depending on the exact module. And on the backside, we connect it to an anode where we capture the signal. We detect X-rays, but what happens when the X-rays hit the silicon chip is that we generate electron hole pairs inside the silicon chip itself. So basically the point of the silicon is to convert the X-rays into electrons. The amount of electrons, or the number of electron hole pairs we generate, will depend on the band gap of the device. And if we have an iron X-ray at 6.4 kV roughly, and assume a electron hole pair of energy of 3.8 eV, we get an iron X-ray generating about 1,680 electron hole pairs inside the silicon chip. If we're looking at boron, though, down in the low energy range, where we only have 185 eV of energy in the X-ray, we're only generating roughly 50 electron hole pairs inside the silicon. And that's what we're actually counting when we count the X-rays, the electron hole pairs. So we really need high sensitivity and low noise system in order to differentiate these very few electron hole pairs inside the device. What we do inside after generating the electron hole pairs is to apply an electrical field or drift field, which basically sweeps the electrons to the anode where we collect the charge. So this is one of the big differences between the older SILI detectors, the liquid nitrogen cooled ones, and the modern drift detectors that we have relatively short distance. The electron hole pairs move through, and we apply a field to sweep them into the anode, which increases the speed with which we can. So if we were to measure the current on the output side of the anode, we would see some peaks depending on when the electrons sweep into the anode, and the peak height will then correspond to the number of electrons and consequently the energy of the incoming X-ray. So here we try to illustrate. We have an iron X-ray, we'll get a relatively large peak, whereas boron X-rays, you have a lot fewer electrons, you'll get smaller peaks on the output. For various practical purposes, we do not measure the current on the output side, but we feed the output of the drift detector into a charge to voltage converter or preamp. And when we amplify the signal and basically let the voltage build up over a capacitor. So we see the plot here is a oscilloscope capture of the direct output before going into a pulse processor. So once we hit a certain preset voltage, we send a reset pulse, which means we ground the circuit and drain out the accumulated charge. So that's what we see here. So for this case, we have about -1 to +1 voltage swing, and then drain the charge once +1 volt. And these steps we see in the output profile corresponds to a single X-ray hitting the silicon chip and being swept into the anode. So since we have the current converted to a voltage, the step height of the voltage corresponds to the X-ray energy. And we, of course, see this takes some time to sweep the full electron cloud into the anode. So it's not a delta function step. It's spread out in time, and the amount of time depends on the silicon device itself, our preamplifier, and all the signal conditioning circuits we have after the device itself as well. One thing to note here is that if we have two electron clouds that arrive at almost the same time, we get a quite asymmetrical peak or increase in the voltage signal we have here. And the voltage increases will tend to overlap, at which point we can't separate them out, and we can't tell what amount of charge corresponds to which X-rays. So this is what we call pileup peaks, and we reject them later on in the measurement chain. So here I fitted the rise function we see here with a Gaussian distribution or an integrated Gaussian. And we can see the electron cloud is not quite symmetrical, not quite Gaussian in shape. There's a bit of a tail that takes longer to sweep in. There's various physical reasons for that. We won't go into the exact details. But if we do the we do the Gaussian fit, we see the rise time in this case is somewhere below 200 nanoseconds. There's a bit of difference between how we define the rise time, whether it's a full width half maximum or a 1090 approach to the signal. But typically you'll see rise times somewhere between 100 to 200 nanoseconds. So of course, this rise time sets the absolute limit for the number of counts you can process with a given device if we assume we can't have any overlaps. If the X-rays are spaced out with less time than the 200 nanoseconds in between, then we can't separate them and we can't process data. So best case scenario, we get all our X-rays lining up perfectly, and you would estimate roughly 5 million is the absolute max you can do on this device. That's not obtainable in reality, since the X-rays don't come in nicely stacked after each other, but in a complete random fashion, so some of them will be overlapping some. But here we have the first ultimate limitation of the technology. How fast can we sweep the electrons into the anode, and that will give us the ultimate limit for our acquisition. In order to analyze the signal assigned to the right energy and discriminate overlapping events and things like that, we take this voltage output and feed it into our digital pulse processor, or DPP. And the way a DPP works is typically by applying a trapezoidal filter where you have a selectable rise or fall time, and in the EDS software we call that the amp time, and then there's a short gap in between the two. There's a few different terms floating around: the pulse processing time, or the rise time, or shaping time, peaking time, and unfortunately they're used a little interchangeably. But in the EDAC software, the amp time corresponds to the rise time, which is the same as the fall time. And the point of the trapezoid is that the height of it will correspond to the voltage input and then consequently to the X-ray energy. When we change the amp time, which can be done in the software, what we're really changing is a averaging time window where we allow the pulse processor to integrate and establish a baseline to reduce the noise inherent to the system. So if we have the 1.92 microsecond amp time, essentially we have two averaging time windows that we sweep along the curve to generate the trapezoidal pulse, and we integrate within that window to average out all the noise. This is why we can discriminate the low sensitivity signals or the low X-ray signals, because we average out and establish the baselines for the noise so we can get a nice discrimination of the actual peak height when we get the voltage jump. So of course, again, we have a limitation here. For a given amp time, there's an upper limit to how many X-ray events we can process per second. Since we only process one X-ray event at a time, and we have here 2 times 1.92 microseconds, which means we have roughly 4 microseconds total process time per X-ray. That gives us an inherent limit to how many X-rays we can process. The faster our amp time is, the more X-rays we can process per second, since we spent less time measuring each one of them. So going to a faster amp time reduces the averaging window, which means we can process more, but we're also averaging less, which means noise will become more dominant in the system. And reducing the amp time, I said that increases the noise, and that comes the most obvious way that transfers into the spectrum is in the detector resolution. We typically define the detector resolution as the full width half max of a Gaussian fit to the manganese K alpha X-ray line, and a lot of literature on how what the terms are that define this. There's a reference down here at the bottom for one of these. But basically, the full width half maximum manganese K alpha depends on the Fano noise, which is a inherent physical limitation around 119, 120 eV, and then the electronic noise in the system. The electronic noise depends on the leakage current in the device, which is inherent to each single device, the system capacitance, and then we have a temperature and shaping time dependent term. So we can see when we change the shaping time or the amp time to a lower value, we will increase the noise in the system and we will get a broader manganese K alpha peak. However, also note that this term with the shaping noise has the capacitance dependence as well, or the capacitance squared. And there's a second term that depends on the capacitance squared. So one of the main driving noise factors here is the capacitance of the system, meaning if we reduce the capacitance, we get better resolution over the entire shaping time range. Reducing the capacitance can be done by reducing the anode size, but we're pretty much at a device limitation there. And then the next big thing that adds to the capacitance is the preamplifier. So here, in our newer detectors, the Element, Elite, and Elect series, we use a preamplifier that's called a Cube. It's a CMOS-based technology. Another reference down the bottom about the Cube technology in specific. And our older detectors, oh, sorry, I see I switched the color coding on that. The older detectors, we use the traditional JFET preamplifier. So please disregard the color coding in that graph there. The two should be switched. So the Cube CMOS is the one that's the lower resolution. We get a significant resolution improvement by switching to the Cube CMOS, and in particular when we go to the very fast shaping times. So these are comparisons for similar modules, similar size. And we can see the Elect, Elite, Element modules in general have quite good resolution, but the degradation in resolution when we go to the fast processing times is much, much less than we saw in the JFET devices, simply because we've reduced the capacitance in the entire electronic noise chain. We still see the amp time dependent term having an effect, so resolution will and should broaden as we go to the faster shaping times, but it's much less dominant than in the JFET device structure. So I said that we have a limitation in the silicon drift device, and we have a limitation in the pulse processor. And in order to get the right data out of the system, we have to match those two up. So here we have a graph of manganese K alpha and the K beta peak, and I took and modified our digital pulse processor to run with a processing time that's faster than the actual rise time. What will happen in that case is that you won't be collecting all the charge in one single window. So you'll get a low energy tail, and you can see here, the faster I go, the more I push it beyond the limits of what the device can do. You get more and more tailing on the low energy side. Another thing to be aware of is that the electron cloud, as it moves through the drift detector, it's slightly elongated or stretched out. That means the rise time will be longer the further away from the anode that the electron cloud was generated. This means in larger devices, larger detectors, you have a spread of the rise time. Hit close to the anode, you will get a short rise time. Hit at the outer perimeter of a large area detector, and you'll get a slower rise time, and that will lead to potential tailing again if you try to run the detector too fast. In this one, I have taken a large area detector and again run beyond the inherent limitation of the device. And if I put a collimator on there to just hit the center area, we're fine. But as I expand the collimator and expose more and more of the chip area, you can see again, you will get tailing. So this is a limitation of larger devices as well. Larger devices, you can collect more counts, but you can't run them as fast as you can with a smaller device, simply because the rise time will be stretched out if you hit the outer perimeter. That being said, in order to see this, of course, you need a DPP that can run the module faster than in its parent limit. If you have a slow digital pulse processor, you will never see this because you never get close to the limit of the device itself. The spectra I show here, I modified our pulse processor to run significantly faster than in anything we ship out. So this is not something you should see on your systems, but it is a limitation in the device technology. We can improve our pulse processors to analyze very, very short amounts of time, but we're still limited by what the actual device can do. So with a bit of talk about what we're analyzing and what limits the speed, I'll hand it over to Tara, and she will go through a few examples.
Very good. Thank you, Jens. That was some excellent insight really into the inner workings of the silicon drift detector and the electronics, the preamp, all important factors in how our detectors work for us to collect our data and to allow us to do our jobs. It's really nice as the technology is improving and increasing so rapidly to stay on top of the relationship between all of the factors that go into the electronics. And especially to hear them from an expert such as yourself, it really gives us a good, keen idea about how it all pays off in terms of data quality. So what I'll be doing today is showing two data examples that demonstrate the relationship between the X-ray counts within a spectrum and the quality of the data that we get with our quantitative analysis. In the most basic sense, the more X-rays that you get into a spectrum, the more statistics that you'll have, and the more statistics that you have leads to better data quality. As Jens showed us, that the new electronics, we can process more counts quickly. So faster amp times mean more X-ray counts per second. And that means more X-ray counts per second throughput, making its way into your spectral data. And within your spectral data, that pays off in terms of allowing the quantitative routines, the software, to best do its thing and turn it into quality concentration values. So the first example is a nitinol sample. It's a common medical device alloy. And this is not a standard, but we do know that the nickel and titanium concentrations have about atomic percent, about 1:1. And with prior investigation, we determined that the target values are about 47% by atomic percent of titanium and 53% nickel. So you'll sort of hear me saying the 53% nickel as the target value, and the examples that we'll show will keep referring back to that 53%. Now, this is also chosen as an example because it represents a relatively easy set of elements. The titanium and the nickel represent mid to high X-ray energies, and there are no overlaps. They're all major concentrations, no minor concentrations. So this is the first easier example. In the data that we could see here, we're looking at keeping the count rate fixed at 10,000 counts per second, and then increasing the collection time. And as we increase the collection time, it brings us closer and closer to the target values. So at about 1 second collection time, we're kind of far from the target values. But then as soon as we go up to the 10 seconds, we get much closer. And as we go all the way up to 50 seconds, our values are, well, actually identical between the two. So we know that between 10 and 50 seconds, we're spending more time, but not necessarily getting anything more in return. And when people ask me how long to collect their data for, I usually say, well, collect as long as it takes to get the data that you're looking for, the target data values that you're looking for. And so with that, then, we look at the 10-second collection time, which gets us as close to the target values as the 50-second collection time does. And now we reproduce this collection. So at 10,000 counts per second for 10 seconds, we sampled 100 times. So we collected the spectra 100 different times. And that allowed us to look at the mean and the standard deviation of the concentration data. And it shows here that we've got a very close to the mean set of values. There's low dispersion in the standard deviation, and most all of the concentration values are close to that mean value of about 53% nickel. As we then move along to a different way of looking at our data, now we're actually looking at total spectral counts within the spectrum itself. So in the previous example, we saw that 10,000 counts per second times 10 seconds, it gives us the data quality that we're looking for as far as target value and low distribution or standard deviation. So now we say, well, that makes 100,000 total counts in the spectrum. Let's see if we could ramp up our count rate and speed up our process time and get the same number of total counts, but do it much more quickly. So is there any trade-off? So now we have 100,000 total counts as our target. The earlier example showed 10,000 times 10 seconds. Now we're looking at 100,000 times 1 second, all for the same total number of counts. The one thing that does change is the amp time. And so the amp time allows us to process the higher count rates more efficiently. The trade-off is that we have a little bit of a drop in resolution. So there's a 3 EV change in resolution. That's kind of the compromise that we deal with in order to work at a count rate that's 10 times higher. And as you can see in the atomic percent, we still achieved close to that 53% target value for nickel, and that's at the 100,000 counts per second. So the small change in EV resolution really didn't impact the quality of the results. Likewise, the 1 second collection time didn't impact the quality of the results either. So when we keep the total number of counts per second as the same, we get very similar results. Now, the one thing that you might notice is that the net intensity value has changed. So if we look at the lower count rate, we get a lower net intensity value. And if we look at the higher count rate, then we get a higher net intensity value. The net intensity is actually reported in counts per second. So that's how we gauge that. It's not the total counts in the spectrum. And now we're going to look at this example in a little bit more of a visual sense. So what we've done here is we've taken that 10,000 counts per second and displayed an overlay of all of the different amp times to take a look at the impact of resolution on the visual spectrum. And we could see here that going through the 7 selectable amp times from the slowest of 7.68 up to the fastest of 0.12 microseconds or 120 nanoseconds, we could see that there is a range of resolutions, and we go up to the fastest process time, which gives us the ability to work at above 1.5 million input counts per second. So also by looking at the spectrum, we could see there is about equal spectral quality peak to background, of course, and also the resolution doesn't change very much at all as we look at really the areas of interest are not just the peaks themselves, but the valleys in between the peaks. So how nicely does the peak come all the way down to the baseline before going up to the next peak? In the example in the center there's the titanium K alpha comes clean down to the baseline before it goes back up to the titanium K beta as even in the fastest process times. And so now we'll look at all of those amp times, that spectra, in terms of quantitative results. So the visual was just the qualitative, and now we'll look at the quantitative results. And I will push it through to the next slide. I'm not getting it on my end, but I hope that the next slide goes through from your end. So on this slide, we're able to look at the spectral counts and resolution, again showing the 10,000 counts per second, but now changing the resolutions through all of the different amp times. And as we look down the value, everything from the 127 EV, which is the slowest amp time and the best resolution for this detector, and as we speed all the way up to the fastest amp time, which is the 156 EV and the 120 nanoseconds, we see that we get target values of atomic percent all very close to the target value of that 53% nickel. And if we look on the graphs, we see that there's low distribution around the mean. Okay, I'm understanding that we have an internet connection issue. We'll put everything on hold for just one moment. So to describe the data that we're looking at here, really the takeaway is that as we push the detector through the faster process times, the data, although you can't see it now, the data is very close to the mean value of 53%. The values are about 52.82 at the slowest amp time to 53.07 at the fastest amp time. And the standard deviation is really quite good. We're looking at about 8% standard deviation. I've got a couple of questions in the meantime, and so until we get our video back, I'll take a question, and it looks like we've got a question about the count rate. And so the question is, what should be the minimum counts per second to obtain reasonably accurate results? Very, very good question. And that is a function of the detector that you have, the electronics that you have, and also certainly to some extent what the microscope can do, what your beam current attainable on the microscope is, and also what your sample can tolerate. So if we think about some of the microscope variables, if we say low kV generates lower count rates and high kV generates higher count rates, that's one illustration. The second way of looking at the microscope impact on count rate is the beam current. And so the beam current is the number of electrons going through the column of the microscope into how many of those electrons are hitting the sample themselves. I've seen Jens's training class. He often cites the number of electrons that are present in 1 nanoamp of beam current. I forget what it is, but it's a very incredibly large number. I think it's 10 to the 19 or something like that, number of electrons. So a lot of electrons in 1 nanoamp of beam current. Those electrons will hit the sample, and a certain fraction of those electrons will excite X-rays within the sample. And so the sample dependency, of course, is what it's made out of. If you have a low atomic number type of sample, then you will generally have more X-rays absorbed within your sample, less escaping. But if you have something nice like titanium, for example, you would have much higher count rates. And so the older generations of detectors, the silicon lithium detectors, the SiLi detectors, would allow us to work just at a few thousand counts per second. Nowadays, with the silicon drift detector, I'm just getting started at 10,000 counts per second. Really, I say to get started, 10 or 20,000 counts per second is a good range. And that's provided that you're working at something from, say, 5 to 20 kV on a moderately conductive material or a material that you're working in variable pressure. And then you should easily be able to adjust your beam current to achieve the 10 or 20,000 counts per second. And so that's why most of the data here was at 10,000 counts per second. And that shows that for the major elements, even as quickly as 10 seconds collection time for a total of 100,000 total counts within your spectrum, you can achieve the target results that you're looking for. Of course, if you do have a nice conductive material, like one of your metals, then you should even be able to move the microscope to a higher beam current. Microscopes are very, very good these days as far as increasing the beam current, but still keeping a small spot size. Usually they are computer controlled, or you can easily open up your aperture on the column. And then, okay.
I think I am on a different internet connection, so I can actually show you different slides. While we just figure it out, I'll just take a question that was for slide 7. So the question was, what's the difference between these two graphs? The top one, there's no change in the detector size. What I'm doing in the top one to introduce the tailing is simply run a given device faster and faster. So changing the processing time beyond the limit of the device. So we can see when my digital pulse processor runs faster than what the rise time of the device is capable of doing, we introduce tailing. In the lower one, I have a large area device and I'm running it fast. But when I am collimating to just hit the center of the device, my rise times are still fast enough to keep up with the digital pulse processor. But as I expose increasing areas of the drift detector, keeping the processing time constant, we can see I end up at a point where the rise time becomes long enough that it's no longer keeping up with the digital pulse processor. So again, we introduce tailing. Two different artifacts. The first one, I'm running the device too fast. And the second one, I am increasing the area to show that once you hit on the outer perimeter of a large area device, the rise time increases and you can end up with problems in the tailing. I'm being told we're back online now, so I believe Tara will take over or pick up where she left off.
Very good. Thank you, Jens. All right, and thank you to everybody who stayed on while we had a little bit of a technical difficulty. So this is the slide that I spoke to, and where we see that as we increase the amp time, speed up the processing, our data stays very stable at around that 53% target value with low standard deviation. And next, we put that into play with really an extreme example. So now we've moved to 500,000 counts per second. And we want to look at, well, how good is the data that we can get when we're using a very fast process time, a very high input count rate. You know, we hear about things like, is that going to shift our peaks, or is that going to give us too much dead time? So what we see here is we could still get at that 500,000 counts per second, still keep a 30% dead time, and a really great resolution of 136 EV, even at those high extreme conditions, which gives us an output of 350,000 counts per second. And we sample the area several times, and again, we see that we achieve very close to the target value, again, with a low variance of the data with a nice low standard deviation. So everything from fast process times to extreme high count rates still gives us good data without compromise. And now we're going to move on to a little bit more challenging of an example. And this is a Ti-64 alloy, which is common in aerospace and also medical devices. This one has both overlapping peaks in our titanium K beta with our vanadium K alpha, and it also has minor concentrations. So we're looking at 6% aluminum and 4% vanadium. So it's a little bit more tricky in a couple different ways. And all of these peaks with the overlap certainly tax the pulse processor and the software routine. So in the first view that we see here, we have the titanium K-alpha and K-beta peaks, along with our vanadium K-alpha peak hidden underneath that titanium K-beta peak. And so we see how the spectral resolution doesn't change very much at all when we look at the overlay. And in this overlay, we're not scaled of all spectra to the highest point, but rather we're looking at, say, the slowest amp time has the least amount of data for any given count rate, and that's because it has the higher dead time or slower processing, fewer X-rays per second. And so the red spectrum, while it has the best resolution, it also has the fewest number of counts. As we speed up the processor, we get a little bit of a drop in resolution from 124, 125, 126, but we're gaining more counts all the while that we go along. And that gives us more counts throughput, more data to work with. I've called out two of the different amp times here, the 124, which we get with a 3.84 microseconds, and 133 EV res with the 0.24 microseconds, because those are the ones that we're going to work with. And that particular detector set was collected with the Octane Elite, which is really the premium performance, which is why we're able to keep all of the resolution values, even at the fastest process time, below 140 EV. So 139 is the poorest that this detector would ever perform at, meaning that we're able to process 750 or more thousand counts per second at our fastest process time, and even with our low energy. So we have some previous examples, previous webinars where we have, say, carbon being detected in a steel matrix at greater than 750,000 counts per second output. Okay. So now we look at the peaks of the 124 EV and the 133 EV, and we see that there is very, very little difference in the resolution appearance of the peaks. But what we'll also see is that we truly will never separate the peaks, the titanium K-beta and the vanadium K-alpha, via actual peak discrimination. So no resolution or pulse processor setting would ever separate those two highly overlapping peaks. So now is where we really need to rely on the software, the algorithm to do its thing. And the software is, of course, going to work best when you have a greater number of statistics to work with the discrimination of which X-ray counts belong to which element. And so with these two different amp times, now we're going to start comparing the actual data that we get from them. But I do also want to change a second variable, and that's where I want to actually speed up the collection time. Because, of course, having two different process times is one benefit. You get more counts per second through. But why don't we do something with that and make our lives and our data more productive? And rather than collect for, say, 30 or 10 seconds, let's see if we could even use that faster process time and collect as quickly as 1 second and still get the good quality data. Or basically, how quickly can we really collect and still get good data? And the example shown here with the quantitative results give a review of the slower and faster amp times. And if we look down the aluminum weight percent column, we see really, really close to target values of the 6%. And as we speed up the processor, we're really not giving any trade-off. We're not losing anything as far as performance goes. So there's a very low distribution between those values, and that yields us a standard deviation the data set of 6.16 plus or minus 0.08 relative for our aluminum, which is really excellent even at the 1 second collection time. Now, the vanadium is the much more challenging peak, and we could see that there is a greater difference from the target value. So with vanadium, we're targeting a 4% value, and we see that we've got a 4.68 mean value with the 4 different collection conditions. But still, our standard deviation is not unduly high for this challenging peak for the peak overlap. And even at the faster process time, if we collect for a little bit longer, the 10 seconds, that's still going to give us a nice value that's close to our mean value or our target value. As we get to the quicker collection of 1 second, then that's where that's the first data point that goes outside of the target value acceptability. But that is 1 second collection time for a minor element overlapping. So if you wanted to stick to the 1 second, what you might also do is increase your count rate and still assure the same data quality for that challenging vanadium overlap quantitative analysis. And with that, I will turn it over back to Jens for some of the really tricky stuff.
So this will also answer a couple of the questions I see has already come in. We will be playing around with high count rates and low energy for this example. So I have an iron sample with moly boride and moly inclusions in the iron. And boron, as you might remember from one of the first slides, is 185 eV, which means it's roughly 50 electron hole pairs. Before anybody cries foul and accuses me of fudging data here, we should remember there's also a moly M line at 192, so it's very close to the boron line, meaning we can't distinguish them in EDS. However, we have done WDS on this sample, and there is boron associated with the moly. Not that it matters too much, because what we're really interested in is the energy sensitivity, not necessarily the specific element, but what range of energies we can actually detect. But this is actually a moly boride sample. If I collect a spectrum at different amp times from this high moly boride inclusion, the bright part in the backscatter image, we see here at the different amp times, 768 microseconds, 192, 048, and 024. And one thing to note is you have some resolution degradation at the fast amp times. You can see at the very fast one, the blue curve, the shoulder on the moly M line is not as distinct. You can't really separate it out. It becomes a peak broadening rather than a distinct shoulder. But it's limited resolution loss you have compared to the previous generation detectors, and that's primarily due to the cube preamplifier having lowered the capacitance in the system. The second problem we encounter, and that was also a question I could see, is that when you go to the 024, there's no boron in the spectrum. And that's because the about 50 electron hole pairs is now comparable to the base noise level that we integrate over the 240 nanoseconds or 0.24 microseconds amp time. So basically, the noise, the variation of the voltage signal within that averaging time window is comparable to the energy of the boron X-ray, which means it will be filtered out in the electronics. So there's two trade-offs when you go faster. One is the resolution, and the other is the base noise level. As that increases, you will start to lose the low energy range because the energy we're trying to analyze becomes comparable to the base noise level. So at 0.24, even though we still have decent resolution, we're no longer able to detect boron simply because of the noise levels inherent to the system. So 048 is the fastest we can go and still detect boron. Here I show the theoretical throughput curves for boron, for the different amp times. And I have added a line in here for each of them showing the 25% dead time. So normally the recommendation is if you want to detect light elements, you want a slow amp time to integrate out all the noise. That is true, but if you have an inherently low noise level, you can still speed up the acquisition, go to a faster amp time, and get good results and more statistics. So comparing the 768 microseconds amp time at 25% dead time to the 0.48, you get 10 to 15 times more data throughput. We can see here at the 25% dead time, we'll roughly be getting 180,000 output counts. We increase our input counts to roughly 300,000. So with that, let's start by looking at the not so interesting maps and compare the 0.48 microseconds and the 7.68 microseconds. So for these, I've kept the collection time per pixel the same, 1.6 milliseconds collection time per pixel. But of course, if I'm at 25% dead time for the 0.48 microsecond dead time, I'll have a lot more counts going through. And as we can see in the spectra, it's quite clear you have better signal to noise in the fast end time where you have a higher throughput. We can see the sample is primarily iron, and we have some dark patches in the iron map, which one of them is the moly. You can see a slight differentiation. There's a slight gradient in the middle of the map where you have a more moly inclusion as well. And we see a couple of other dark spots that shows up as aluminum oxide. This is probably holes in the sample and me not being careful enough to clean out all the polishing compounds, which is typically alumina. But we can see the inclusions quite clearly. But if you compare the iron map, you can see the slight gradient in the concentration seen in the middle of the map is not as clear at the 768 microsecond statistics. So moving on to the maps of interest, the moly L line and the boron K line. Again, we compare the 768 microseconds at 25 dead time and 0.48 microseconds at 25 dead time. And we can see the high moly concentration inclusion shows up in both. So that we can easily differentiate even if we have low count numbers. If you look careful enough in the 0.48 microseconds, you can see the slight gradient where you have a slight moly enrichment. But the boron map is really where it is clear that the high count rate gives you a benefit. Yes, you might have better better resolution at the 768 microseconds, but you also have very few counts. And high resolution noise is still just noise. At the 0.48 microseconds, we start to see clearly the high concentration inclusion and also the gradient of moly in the less intense part of the map. This is just the raw count numbers plotted. Often when we do maps, we do some various filtering and try to pretty up the pictures, do a contrast brightness stretch, and maybe do some despeckling. And I applied the same filters to both maps to make them pop a little more. And you can see even if you do image processing, in the moly you can bring out the high concentration inclusion, but in boron it's very low signal to noise ratio. And even no matter how much you filter it, you're not gonna see the gradients in there. It's not magic, it's not TV where we can just zoom into a image and generate artificial pixels. The data is what the data is. And at high count rates, you get better statistics to the point where you can actually see what is going on in the sample. And again, to highlight what is actually going on in the individual spectrum level, slow amp time, low throughput still gives you the high concentration inclusion, but if you try to look at the individual pixels, you run into the limitations. The first curve here on the left, I took the high count rate map, the one at 0.48 microseconds at time, 25 dead time, and compared it to the low count rate, the one at 7.68. And I extracted a spectrum from the same pixel in this moly boride inclusion. And you can see at the low count rates, I have about 2 counts at iron, whereas I have about 17 counts in the high count rate. And my boron peak, I actually have no counts in the low count rate, whereas we start to make out a peak in the high count rate. And take into account this is 1.6 milliseconds acquisition time. So it is rather noisy, of course, because of the low acquisition time, but we can still pull out meaningful data. On the right-hand side, I show a line profile extraction across the region for moly and boron in both the high count rate and the low count rate maps. And we can see that there is an increase in the high count rates, whereas the low count rate, it's close to noise levels, whatever is going on. Now again, this is 1.6 milliseconds, so this means I acquired my boron map in a couple of minutes. Most of the time, mapping boron is something that takes a significant amount of time, and increasing my acquisition time, of course, will give me better statistics. But the point of it is to show that going faster gives significant benefits for light elements as well, as long as you can distinguish them above the noise level in your pulse processor, and you actually get meaningful data in a very short amount of time. We've always pushed faster, higher count rates for mapping, and that works very well when you have the high energy lines, as Tara was showing with nickel, titanium, vanadium. That's easy enough. The tricky part is the low energy range, where we now can run very, very fast on these very light elements as well, and get meaningful data out based in good statistics in a short amount of time. So to summarize things, the throughput, however many counts we can get into our spectrum, is limited both by the drift detector itself and the digital pulse processor, and they must be matched up if you want to avoid artifacts in your spectra at high count rates. Having high count rates coming into the system is not necessarily a good thing on its own. It's the throughput that matters. So you need to select the right processing time on the digital pulse processor to actually put your input count rates into output count rates. I have seen people very happy that their systems can do 800,000 input counts until I point out that those are just input counts. You're only getting about 10,000 counts out of the detector because you're saturating it. So these things need to be balanced in order to make any sense. We, in our newer detectors, use a new preamp based on CMOS technology, which has lower capacitance, and that allows us to do high throughput acquisitions without the significant resolution loss that that's traditionally been the big trade-off. So this means we have low noise electronics, and that is also what you need in order to do low energy with high throughput. And because of this, even light elements like boron can be mapped with over 200,000 counts throughput without a significant loss of quality in the data. This means that you will get better statistics in the same amount of time, or you can acquire your maps much, much faster. If we were stuck with the 768 microseconds, we would probably have to run a map for about half an hour to see the boron distribution, which can now be done in few minutes. And besides just the time constraint of it, increasing the total number of counts going to a higher throughput in your spectrum maps leads to higher quality data. So the quality of your data set depends on both the detector resolution and the number of counts in there. Having good resolution with low count numbers doesn't give you anything. Having high count rates but with bad resolution is not good either. They need to be balanced out, and this is what we're able to do. So you can do fast acquisitions, high statistics in a short amount of time, and build up your spectra to give high quality data. Due to the fast processing time, you can also increase the total number of counts in the spectra without increasing your collection time. Just switching to a faster pulse processor time will give you a higher throughput of data. You will lose a little bit in resolution, but most of the time that's easily compensated by the increase in statistics. And again, mapping high throughput generates good statistics. Most of the time we just use maps to illustrate where the distributions are, show pretty pictures basically. But with good statistics, you get to the point where you can extract quality data even on a limited pixel basis. when we have small inclusions in there that are just summing up a few tenths pixels or so, high count rates will make the difference between determining what those inclusions are and just having them drown out in the noise of a low count statistic map. So again, high count rates can bring up those details in the spectra you're not able to see for the same acquisition time at the lower pulse processing time. With that, I'd like to thank you for your attention, and I apologize for the few issues we ran into. And let's go on and look at some of the spectra we have here. Oh, sorry, not spectra, questions. That's what happens when you read and talk at the same time.
Jens, I'd like to take one of the questions that somebody had asked about the slide that I showed, the 7 selectable amp times overlay. So those were collected at 10,000 counts per second for collection time of 10 seconds. And so you can get very nice looking data like that, nice looking spectra in just 10 seconds at moderately low count rate and without really any statistically or grassy looking spectra. There were a couple comments on some of the differences with the low energy lines dropping out, and that is the difference between, say, our entry-level element and our premium resolution elite. So with the elite detector, you're going to be able to keep the detection of your K and L lines for most of your elements throughout the range of collection time. There was a previous webinar where we showed carbon being collected at greater than 750,000 counts per second output. That's usually a function of the premium level detectors. Another comment was about the impressive detector performance, and I agree completely. I've been at EDS for 20 years, and these are the coolest detectors, really the most impressive detectors that I've ever worked with. So it's been a lot of fun these days, especially breaking the stereotypes where people have said that most applications will never see over 100,000 counts per second or more, but with these detectors, clearly we can do it, and the examples that we showed, we're able to get the quality quantitative results and the nice mapping images and data from the maps as well.
So I just switched to slide 11. This one shows the same thing as I was saying with the boron map, but once we go to our very fastest amp time, the 120 nanosecond integration window, we get quite a bit of noise in the spectrum we can't filter out, and we see that as a low energy cutoff. So this is why, like, the boron line disappeared. This is not the premium detector we're showing for this one. And we can see here the titanium line is comparable to the noise level, the titanium L line, once we go to the extreme fast amp time. So when you look at the premium detectors, one thing is the detector resolution. As I showed you, the resolution is a function of the electronic noise in the system, meaning that if you have a detector with a broad peak and manganese K alpha, that will also mean it has more noise inherent, and when you try to go faster, you will see a low energy cutoff earlier simply because of the base noise levels. So good detector resolution buys you two things: good resolution and a low noise system. There's a question about the peak broadening, whether it will affect the quantification numbers, and this is part of what Tara was highlighting, that if you have a fixed input count rate or fixed output count rate, that is, of course you'd like the better resolution, but we normally don't just change the amp time and stick with the same output count rate. Going to a faster output count rate, faster amp time will give you a better output count rate, which means your statistics increase. So the quantification numbers depend on two things: the resolution and the statistics in there. If you have good resolution and good statistics, that's the ideal situation. But often meaning good resolution means that you'll run slower and your statistics will be more limited. Most of the time, more counts is really the way to go. The peak deconvolution routines are usually quite efficient at compensating for the broader resolution. And we're talking about 125, 127 EV now at the slower amp times, and compare that to the silly detectors where we are happy if we got 130 or 140 EV. So it's a matter of both resolution and statistics. Most of the time, statistics is the more important part of it, which you can get by either increasing your acquisition time or by going to a faster amp time and or increase your beam current. There are, of course, some of the inherent overlaps which are tricky, whereas resolution might be able to help you in the beginning, but again, statistics wins out. Something like the moly sulfide overlap is one of the ones that's inherent, and no matter how slow you go, your resolution won't really help you much. You need good statistics in order for the model to separate that overlap, meaning better counts. There's also a question about which lines are used for quantification. In general, we recommend to use the highest energy line available because there's typically less peak overlaps and less background contribution in those ranges, but it can be selected in the software. Generally, whichever line you click and add into the spectrum is the one used for quant. We also have a table in the periodic table window where you can select exactly which lines you want to use for quantification. So it's not like you're stuck with one line. There's the option to change them from the use. Generally, we recommend higher energy lines for quantification because there's less overlaps and better background signal to background ratio.
All right. I think we got all the questions, right? So this webinar has been recorded, and it will be available for distribution in about the next day or two. If you've registered, you'll get the follow-up information. And also, there are a series of supporting documents that go along with this that you might download from your widget area. So feel free to download those and look through them. Give us a holler, send an email following the webinar if you have any questions. And as always, it's great working with you, Jens. This was a fun one together. And thank you to Sue for organizing. I think this will conclude our webinar. Thank you.